Okay, so where are we in the schedule? We are following the schedule that I handed out as part of our syllabus here, all right? Okay, so today is, it's hard to keep track of the days. Today is Thursday, October 15th. We're in the middle of October. It's day 18. Remember, on my YouTube channel, I'm going by day number, all right? Okay, so we're about halfway through, all right? I'm grading the chapter 1 homework first. I do expect to have that returned next week. And also next week, Friday, is going to be the withdrawal deadline. Now, this is true of your normal 16-week classes where after this deadline, Friday of next week, then you're committing yourself to a grade in the class, basically. And then if you drop by then, you have a W in your transcript. So it is imperative that I return graded items by then. All right, so I'm starting with chapter 1 homework first. Okay, now regarding the chapter 4 homework, it's the shortest chapter. In a way, it's kind of my apology homework for the 2-3 because 2-3 is kind of long. So the chapter 4 stuff, so chapter 4, we're going to finish up chapter 4 next Tuesday in lecture. So all that will be due a couple of weeks from now. It's going to be due on Wednesday, October 28th. Okay, which is about a couple of weeks from now. Okay, so we're going to finish the lecturing on chapter 4 next Tuesday the 20th. The withdrawal deadline is Tuesday the 23rd. I will have something returned by then. And then the homework session for chapter 4, the big one, will be 2 Tuesdays from now on the 27th. And the homework for chapter 4 is due Wednesday the 28th. It's one of the smaller homework assignments. It's meant to balance out the 2-3. Like, for example, when people had exams, the 2-3 exam was pretty intense. The chapter 4 exam tended to be easier. So it was sort of a balancing effect. All right. So we are following the overall schedule of the syllabus. All right. Any questions thus far? Let's see. Any questions thus far? All right. Let's see. Okay, so let's continue on with graphing trig functions and then inverse trig functions. Go ahead and chat, ask questions in chat. Let's begin. We are recording. All right, good. All right, let's begin.
Hi, everyone. We're going to graph other trig functions beyond sine and cosine. In section 4.6, we're going to start with graphing y, or f of theta, equals tangent of theta. A key thing to remember, tangent is what? Tangent is slope. That's a great thing to remember. Tangent is slope. So for example, what is the tangent of 0 radians or 0 degrees? The tangent of 0 is 0, which I'm indicating in purple here. I'm going to indicate the tangent values in purple. Remember, these are the slopes of these terminal sides. The tangent of 0 is 0. When theta equals 0, tangent is 0. The tangent of pi over 4 is 1. Think of the line y equals x. The tangent of pi over 4 is 1. And as we increase from 0 up towards pi over 2, the corresponding slopes are increasing from 0 up towards infinity. Likewise, as we go backwards, clockwise, from 0 towards negative infinity, the tangent of 0 is 0. Once again, the tangent of negative pi over 4 is negative 1. As we decrease the angle towards negative pi over 2, the slopes become negative 2, negative 10, let's say, negative 100. The slopes are approaching negative infinity. And it turns out that we capture one cycle if we consider the open interval from negative pi over 2 to pi over 2. I'll discuss that in a moment. In the meantime, let's frame one cycle. All right. Now, one key difference from sine and cosine is that we're going to place our pivot, which corresponds to the origin. We're going to place our pivot right at the smack dab center of the frame. For sine and cosine, we would place the pivot at the left center of the frame. But among the 6 trig functions, tangent is the only one for which we put the pivot at the center. We're going to place the origin at the center. Bottom line, the key benefit of this is that we can represent a cycle by a single unbroken snake. All right, now let's see why the graph of this snake makes sense for one cycle of y equals tangent of theta. Well, again, tangent of 0 is 0. That explains why 0, 0, the origin, is on the graph. Tangent of pi over 4 is 1. That explains why this quarter point is on the graph. As the angle increases from 0 towards pi over 2, as the angle increases from 0 to pi over 2, theta, the tangent value increases towards infinity in terms of the y-coordinate. Now going backwards, tangent of negative pi over 4 is negative 1. That explains why this point, negative pi over 4, negative 1 is on the graph. It's a quarter point or key point. And as the angle approaches negative pi over 2, as theta approaches negative pi over 2, from the left, the tangent values, the slope values approach negative infinity.
I should have said from the right. You're approaching negative pi over 2 from the right, actually.
The y-coordinates, the tangent values, approach negative infinity. By the way, this all makes sense because remember, tangent is what kind of function? Tangent is odd, meaning the graph, including the cycle, is symmetric about the origin. If you take this snake and rotate it 180 degrees about the origin, you get the same snake. That explains, for example, why tangent of negative pi over 4 is negative 1, while the tangent of positive pi over 4 is positive 1. These 2 points are symmetric about the origin. These 2 points are symmetric about the origin. The graph of y equals tangent of theta is odd. And notice that when we graph this one cycle, we get 3 key points or quarter points, and we have 2 VAs, 2 vertical asymptotes at the edges, corresponding to theta equals pi over 2 and negative pi over 2. This here is our fundamental cycle for y equals tangent of theta. If we repeat the picture, we get another cycle, a snake, from pi over 2 to 3 pi over 2, over here in dark blue. We have another snake here in purple from negative 3 pi over 2 to negative pi over 2. Again, the period for y equals tangent of theta is not 2 pi like before, it's only pi. The period is pi. The width of each cycle is pi units. Remember, the period is the width of a cycle, the thinnest piece of wallpaper, such that when you repeat it infinitely far in both directions, gives you the result of the entire graph for y equals tangent of theta in this case. What's another explanation for why the period here is pi? Well, look at the unit circle. Again, the period is pi, not 2 pi like before for sine and cosine. Well, look here. Think slope. Tangent is slope. As we go from negative pi over 2 to pi over 2, the angle theta, as the angle theta goes from negative pi over 2 to pi over 2, what happens to the slope? The slope goes from very negative to slightly negative to 0, tangent of 0 is 0, to slightly positive to very positive, very steep slopes, like a million, a billion. So we have this pattern of slopes or tangent values from very negative to very positive, covering this interval from negative pi over 2 to pi over 2. That's an interval of width pi radians. We have a distance of pi radians between negative pi over 2 and pi over 2 radians. But what about the pattern of slopes going from pi over 2 to 3 pi over 2? Well, again, it's the same pattern as from negative pi over 2 to pi over 2. We get slopes that are very negative, slightly negative, tangent of pi is 0. Then we get slopes that are slightly positive, and then slopes that are very positive, like a million or a billion. Remember that we always read slopes here left to right. So we have a negative slope or tangent value in quadrant 2, and we have a positive slope or tangent value in quadrant 3. But notice that this pattern of tangent values or slopes, again, we go from very negative to very positive, just as we did from negative pi over 2 to pi over 2. So basically, a half circle will give us a complete interval of behaviors for the tangent function. Very negative to very positive, and we get a repetition from here to here. So the cycle is only pi, not 2 pi. We don't have to go all the way around the circle to get a complete interval of behaviors for tangent. I would like to explain this frame in greater detail and how it's similar and different from the frames for sine and cosine that we did in 4.5. So what are some similarities? Well, again, we have this candy bar, this Kit Kat bar, 3 horizontal line segments this way, 5 vertical line segments this way. Those are similarities. We're going to get some key points on these intersection points. But there aren't too many similarities beyond that. We do split the period up into quarters. That's another similarity. But we more often notice the differences. What are some key differences with the way we frame this cycle? I'll do this. I'll put the writing over here and put the frame over here. All right, so what are some key differences? First of all, when we graph a tangent function, I should write out tangent here. When we graph a tangent function, the central point, the center point, not the left center point of the frame, will be our pivot, which here is the origin. And then later on, when we do translations and other transformations, it'll move around. But the pivot is at the center of the frame, not the left center like before. Also, the left and right edges of the frame correspond to vertical asymptotes, VAs. Graphs for our classic sine and cosine functions from section 4.5 did not give us any asymptotes. Here, we do get vertical asymptotes. In fact, we get them periodically, every pi units for the overall graph. And again, if the pivot is at the center, the VAs for tangent will be at the edges. Now, unlike for sine and cosine, the graph of a cycle will stretch beyond the frame and approach asymptotes. So sine and cosine graphs were trapped within the confines of the frame. They were waves. But these tangent snakes are going to break out of their frames, and they're going to approach these VAs at the edges. Notice that the range here will be what? The range here will be all real numbers. That was not the case for sine or cosine, the ones we did in 4.5. The cycles, again, are shaped like snakes, not waves. Although we do have these periodic cycles, we have a zoo of snakes separated by VAs, vertical asymptotes. And we have no maximum or minimum points. We do have inflection points. We do have these quarter points over here, but we don't get any max or min points for these tangent graphs, as we did for sine and cosine. Remember, sine and cosine waves were trapped inside the frame. These tangent guys are not. The range is all reals. For the tangent snakes that we draw, at least the way I do them, we get 3 key points and 2 VAs. Although if you move the pivot to the left center, what ends up happening, if you were to move the pivot at the left center, if pivot at the left center of the frame, like we did for sine and cosine, what ends up happening is that you get half a snake, a VA in the middle, and half a snake over here. We do get key points at the ends. So we end up with a half a snake, a VA, and half a snake. We would get quarter points also over here and over here. So what ends up happening is that if you put the pivot at the left center, like we used to, then we would have 4 key points and a VA right in the middle. But then we get this pair of half snakes. And although that is legitimate, this would represent a cycle for tangent of theta. It's not as appealing visually. I think generally speaking, we would prefer one unbroken snake as a cycle as opposed to these 2 half snakes. That seems a little gross, to put it mildly. Okay, so next time we're going to talk about domains, ranges, and equations for these vertical asymptotes. Next time.
All right. So before we go on, well, here's a little meme for a tangent. This was cute. So that's a hideous tan line. Tangent cycle. All right, so we're going to talk more about the tangent function over here. Any questions? Any questions? All right. So the next video will be about 10 minutes.
Hi, everyone. We're now going to talk about the domain, range, and vertical asymptotes for y equals tangent of theta. Now, in fact, we've talked about the range before. Let's review that. What are the possible real numbers we get as slopes, as tangent values? Well, all real numbers. Because a tangent value or slope can be 0, positive, like 1, 2, a million, a billion, or any negative real number, -1, -10, -a million, -a billion. Any real number can be a slope, so any real number can be a tangent value. If you look at even just one cycle, remember the y-coordinates here are the tangent values, the y-coordinates here are the slopes on the unit circle. The y-coordinates here are the slopes on the unit circle. And again, what are the tangent values we pick up? We pick up all real numbers as y-coordinates, as tangent values. That's why these snakes are infinitely tall in both directions, up and down. Any real number can be a slope. The tangent is all real numbers. Now, I'm going to discuss the vertical asymptotes, or VAs, for the graph of y equals tangent of theta, and then we can figure out the domain. First, the vertical asymptotes. So here's the key thing. Where is tangent of theta undefined? Where is tangent undefined? So in particular, the slope of what kind of a line is undefined? The slope of what kind of line is undefined? The slope of a vertical line is undefined. So imagine this vertical line going through the origin. We're going to have a problem at angles corresponding to the North Pole up here and the South Pole down there. Tangent, slope, is going to have a problem. Tangent will be undefined at the corresponding angles. Well, what angle do we typically associate with the North Pole of the unit circle? Typically, pi/2. Tangent of pi/2 is undefined. And what angle or angles do we typically associate with the South Pole? Well, negative pi/2 is one, 3 pi/2 is another. In fact, there are infinitely many angles where tangent is going to be undefined for both the North Pole and the South Pole. Pi/2 and its coterminal angles, and 3 pi/2 and its coterminal angles. So how do we get from problem angle to problem angle? Start with pi/2. Pi/2 plus how much will give us 3 pi/2? Pi/2 plus pi radians will give us 3 pi/2, because that's half a revolution around the unit circle. And then we do another half revolution to get another problem angle, 5 pi/2. So we keep adding pi radians, or we could subtract pi radians in this direction to get these problem angles. Going back to this larger graph for y equals tangent of theta, where were our problem angles? At theta equals pi over 2, 3 pi over 2, and then 5 pi over 2, 7 pi over 2, and so forth. Going backwards, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so forth. We have infinitely many VAs. And where are the problem values? Tangent of theta is undefined if and only if theta is of the form pi over 2 plus pi n, where n is some integer. Another way you can write that, where n is in the set Z. In fact, we'll usually write it that way, where n is in the set of integers. We have a problem. Tangent is undefined when theta is of the form pi over 2 plus 0 pi plus 1 pi plus 2 pi, and so forth. Also, minus 1 pi, minus 2 pi, and so forth. N could be 0, a positive integer, or a negative integer. We do not need plus or minus. Now, if you notice the angles, the values for theta in radians for which we have a problem, where tangent of theta or slope is undefined, remember, it was 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth. Also, negative 1 pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2, and so forth. So another way to write this is to factor out pi over 2, and don't worry about this, but you could factor out pi over 2, and you get 2n plus 1 all times pi over 2. In chapter 9, we're going to see that 2n plus 1 represents odd integers if n sweeps out over the integers. So we have a problem when theta is an odd integer multiple of pi over 2. For example, 1 pi over 2, 3 pi over 2, and so forth. Also, negative 1 pi over 2, negative 3 pi over 2, and so forth. In any case, these are the equations for the VAs, the vertical asymptotes of y equals tangent of theta. Every vertical line of the form theta equals pi over 2 plus pi n. Where are the problem values? At theta equals 1 pi over 2, 3 pi over 2, and so forth. Theta equals negative 1 pi over 2, negative 3 pi over 2, and so forth. So these will give us all the VAs for the graph of y equals tangent of theta. Another way of seeing that, not only are these the places where tangent or slope is undefined, at the North Pole and the South Pole, there's another way of looking at this, in blue. Remember that tangent of theta, by the quotient identities, is sine of theta over cosine of theta. Where do we have a problem? We have a problem when cosine of theta is what value? We have a problem when cosine is 0 in value, when the bottom is 0. Well, think about the unit circle again. Think about the unit circle. I'll go up here. Think about the unit circle. Where is cosine 0? Where is cosine equal to 0? Cosine is like the x-coordinate on the unit circle. Well, where's the x-coordinate equal to 0? Again, up at the North Pole and at the South Pole. So there are two ways of seeing why we're going to have problem angles at the North Pole and at the South Pole, because the slope is undefined over here for this vertical line, and also because the cosine value, the x-coordinate, is 0 at the North Pole and the South Pole. So those are two ways of seeing that we're going to have problem points at the North Pole and the South Pole, corresponding to these angles. Now, if these are the angles for which tangent is undefined, what's the domain? Be careful. The domain of the tangent function is the set of all real values of theta. Nowadays, I like to write this. The set of all values of theta in the reals. I like to put in the reals. The set of all theta values in the reals such that theta is, take a look at this. I'll put this in red, such that theta is not of the form. Is not the form. Pi over 2 plus pi n. Remember, these were the angles that gave us VAs. The domain is the set of all angles, theta, such that theta is not where we have a VA, not of the form, pi over 2 plus pi n. Don't forget to slash the equal sign. In other words, theta is not like 1 pi over 2, 3 pi over 2, and so forth. Again, this is the domain for the basic tangent function. It's all real values of theta where we do not have a VA, do not. Don't forget to slash the equal sign. Next, we're going to discuss cotangent of theta. And don't forget, the range was all reals. We mentioned that before. The range is also all reals for cotangent, as we'll see.
All right, any questions before we go on to cotangent? Okay, because it's good to have a foundation with tangent before you go on to cotangent. Any questions? Any questions? All right, let's go on.
Hi, everyone. We're now going to go from tangent to cotangent. And what are going to be some similarities between these two functions? So, similarities between cotangent of x, say, and tangent of x. Well, for one thing, their graphs are both going to be snakes. The period will be pi for both functions, and the VAs are pi units apart. Remember that for tangent, the basic tangent graph, the VAs here were pi units apart. And that was, in fact, the period. As a piece of wallpaper, period is pi, period is pi, period is pi. And there are pi units between the VAs. The same will be true for y equals cotangent of theta or x. Now, one warning, if you consider cosecant of x and secant of x, we're going to see that, again, VAs will be pi units apart, like for cotangent and tangent. However, but the period will be 2 pi for those later two functions, and also the graphs will not be snakes. But it is true that for the graphs of cotangent, tangent, cosecant, and secant of x, we are going to get pi units between the VAs. That also means that you're going to have pi units between the exclusions from the domain. All right. Now, how do we get from the graph of y equals tangent of theta to the graph of y equals cotangent of theta? Now, don't freak out about this, but we can consider these transformations. So what is cotangent in terms of tangent? By the cofunction identities, cotangent of theta is equal to tangent of the complement, pi over 2 minus theta. Remember that according to the what I call the switch rule for subtraction, b minus a is the opposite of a minus b. So when we switch about the minus sign to get the theta in front, pi over 2 minus theta, that equals the opposite of theta minus pi over 2. And what can I do with this -1 factor on the argument? Tangent is what kind of function? Tangent is odd, which means that this -1 factor on the argument can pop out. Cotangent of theta is equal to the opposite of tangent of theta minus pi over 2. And right here we have a recipe to get from the graph of y equals tangent of theta to y equals cotangent of theta. Remember section 1.4 on transformations. In particular, if we substitute theta with theta minus pi over 2, I'll put that in red. If we substitute theta with theta minus pi over 2, what happens? We take tangent of theta and we substitute with theta minus pi over 2. We substitute. What happens? That leads to a horizontal shift. A horizontal shift to the right by pi over 2 units. We shift to the right by pi over 2 units. Although it turns out that shifting left would yield the same graph, technically we shift to the right by pi over 2 units. And if we multiply all this by -1, what happens? We flip the graph. We reflect the graph about the horizontal axis, say the theta axis. We do a flip. So how can we get from the graph of y equals tangent of theta to the graph of y equals cotangent of theta? We take the original tangent snake graph, shift right by pi over 2 units, and reflect, flip, about the horizontal axis. So, bottom line, we shift to the right by pi over 2 units, and we reflect about the horizontal axis. So you see, these tangent snakes shift right, the VAs also shift right by pi over 2 units, and these rising snakes flip over and become falling snakes. We have a shift and a reflection to get from the tangent graph to the cotangent graph. Still, the period is pi units, and the VAs are still pi units apart. The range is still all reals. That does not change either. Okay, so how do we graph one cycle for y equals cotangent of theta? Well, remember, before for tangent, we had VAs at theta equals -pi over 2 and theta equals pi over 2, corresponding to the north and south poles on the unit circle. But now, we're going to take these VAs and shift them to the right by pi over 2 units. So -pi over 2 goes to 0, and pi over 2 goes to pi. Over here, we have VAs at theta equals 0 and theta equals pi. As a result of that, the pivot is not at the center as it was for tangent. We're back to the left center, like for sine and cosine. We associate the origin now with the left center point on the frame, as we did for sine and cosine, although this point will not be a point on the graph. We have our frame here. We have VAs at theta equals 0 and theta equals pi. Instead of a rising snake, remember, we have a falling snake. So we pick up these 3 key points here, tic-tac-toe, but they're falling this time. And we have VAs to the left, so the snake rises to the left. We have a VA on the right here. The snake falls to the right VA over there. It's a falling snake with 3 key points tic-tac-toe along this diagonal. For tangent, we went tic-tac-toe along a rising diagonal. So here are 3 cycles for y equals cotangent of theta. Again, the period is pi units, and we have pi units separating the VAs. But unlike tangent, we have VAs at 0, 1 pi, 2 pi, integer multiples of pi, and these are falling snakes, not rising snakes. But like tangent, cotangent is odd. So we do still have symmetry about the origin. If you take this graph and rotate it 180 degrees about the origin, you get the same graph. All right. Now, there's another way of looking at the relationship between tangent and cotangent. One is from the cofunction identities, where we got the ideas of shifting and reflecting, but we can also look at these 2 functions as reciprocal functions. And we're going to devise principles of reciprocal trig functions that we're going to apply later when we discuss y equals tangent of theta, y equals cosecant of theta, and y equals secant of theta. So what are these principles of reciprocal trig functions? Okay, Now, when tangent is zero, what is cotangent? What is 1 over 0? 1 over 0 turns out to be undefined. So remember that whenever tangent is 0, cotangent is undefined. We have a VA. When tangent has an intercept, tangent is 0, tangent is 0, tangent is 0, over here, and over here. These correspond to VAs for the cotangent graph. Intercepts for the tangent graph correspond to VAs for the cotangent graph. When tangent is 0, cotangent is undefined. And also vice versa. When cotangent is 0, tangent is undefined. When cotangent has a theta intercept, tangent has a VA. So intercepts, theta intercepts for one graph lead to VAs for the other graph. So for these reciprocal trig functions, remember that one function is 0 in value if and only if the other is undefined. That is, we have an intercept, like an x or theta intercept for one graph, when we have a VA for values of theta, where we get VAs on the other graph. Okay, now what about sines? Well, the reciprocal of a positive value is still positive. For example, in quadrant 1, all these guys are positive, right? When tangent is negative, so is cotangent. A reciprocal of a negative is a negative. So as far as reciprocals go, positive goes to positive, negative goes to negative. Positive to positive, negative to negative. So reciprocals have the same sign for the same value of theta. Okay, in between the VAs and the intercepts, the zeros. So between the VAs, where the functions are undefined, and the intercepts, where the functions are 0, the values of reciprocal trig functions have the same sign. For example, in quadrant 1, both tangent and cotangent are positive. In quadrant 2, between pi over 2 and pi, both tangent and cotangent are negative. For tangent, we're crossing a VA. For cotangent, we're crossing an intercept, a 0. Same sign. To make things cleaner, I'll erase these now. All right. What about increasing versus decreasing? Again, between intercepts and asymptotes, as one function increases, the other function, look at this, decreases. For example, in quadrant 1, tangent increases, slope increases as you go from 0 to pi over 2. But cotangent decreases. Think about this. Let's say that tangent is going from 1 to 2 to 3. The slopes are going from 1 to 2 to 3. What's happening to the reciprocals? The reciprocals are going 1, 1/2, and 1/3. So as the tangent values increase, the cotangent values, the reciprocal values, decrease. They go in different directions. In quadrant 2, tangent is still increasing, but cotangent is decreasing. In quadrant 3, well, tangent is increasing along these snakes, cotangent is decreasing along its snakes. So in between the asymptotes and the intercepts, as one function increases, the other decreases. As one function increases, the other decreases. I'll put this in purple. As one function increases, the other decreases, and vice versa. They go in different directions. Again, that corresponds to the fact that tangent has rising snakes, while cotangent has falling snakes. Also, they have the same period. For example, you can see that you have pi units between the VAs, and the snakes have width pi units. But as I mentioned earlier, we're going to see that for the cosecant and secant graphs, that, again, the VAs would be pi units apart, but the period would be 2 pi and not pi. Those graphs will not be snakes anyway. Okay. So let's talk now about domain, range, and vertical asymptotes. First off, the range. You can see that the snakes are going to be infinitely tall, both up and down, so it's not surprising that the range is going to be all reals, like for tangent. But the vertical asymptotes and the domain are going to be shifted by pi over 2 units. So remember, because cotangent of theta by the reciprocal identities is 1 over the tangent of theta, cotangent is undefined. Cotangent is undefined if and only if tangent is 0. Cotangent is undefined exactly when tangent is 0. When is tangent or slope 0? Well, we're going to have our problem points at the east point and at the west point, corresponding to this horizontal line through the origin. Slope or tangent is 0 at the east point and the west point. And what are the angles that we associate with the east point and the west point? Well, angles like 0, pi over here at the west point, back here, 2 pi, also 4 pi and 6 pi, and the opposites. Over here, we have problems at 1 pi. We have problems at 1 pi, 3 pi, 5 pi, and so on, and their opposites. Basically, integer values of pi. We're going to have problems at integer multiples of pi. Integer multiples of pi. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, and so forth, and also their opposites. -1 pi, -2 pi, and so forth. Those are our problem values for theta. That's where tangent is 0 and cotangent is undefined. Cotangent of theta is undefined if and only if tangent of theta, the slope, is 0. That's where theta is pi n, integer multiples of pi, where n is some integer. N is in Z. The set of integers. Half revolutions. The problem angles are separated by half revolutions, just like for tangent, where we had problems at the North Pole and the South Pole. Again, another way of looking at that, if you tear apart cotangent, cotangent of theta was cosine of theta over sine of theta by the quotient identities. Tangent had a problem when cosine was 0. Cotangent has a problem when sine is 0. And where is sine 0? Where's the y-coordinate 0? The y-coordinate is 0, again, at the west point and the east point. Another way of seeing that those are the problem points, and these angles here are the problem angles, because we do not want y to be 0. Sine to be 0. Okay, so cotangent is undefined when tangent is 0, the slope also when sine is 0, the y-coordinate on the unit circle. Either way, here are the problem points. The domain, therefore, is a set of all theta in the reals such that theta is not, remember, is not of the form pi n for integer values of n. Here's the shorthand. The range is all reals, just like for tangent. Infinitely tall snakes, up and down. All right. Next up, we're going to graph tangent and cotangent functions more generally using picapia, the frame method. And we'll talk about that next time.
Okay, so we dealt with the basics for tangent and cotangent, domain, range, graph, the basic functions. Any questions? Any questions? We're going to do transformations now.
Hi, everyone. We're now going to graph tangent and cotangent graphs more generally for transformed functions. So we're going to go back to the frame method, picapia. And I'm going to discuss the cycle grid. What are the possible cycles that we're going to draw in our frame method? Well, it depends if we have tangent versus cotangent, and if the value of A, which is the letter before tangent or cotangent, the number before tangent or cotangent, it depends if it's positive or negative. We're going to graph equations of these forms here. A is like a coefficient before tangent or cotangent, and it matters, like before, if A was positive or negative. A cannot be 0. If A is positive, then all is good. We have rising tangent snakes and falling cotangent snakes. But if A is negative, then we flip. So tangent goes from rising to falling, and cotangent goes from falling to rising. So basically, for tangent and cotangent graphs, we're either going to get a rising snake going tic-tac-toe through these 3 key points, or a falling snake going tic-tac-toe through these 3 key points. Remember that for tangent, the pivot corresponding to the origin, maybe where the origin used to be, that corresponds to the central point of the frame, while for cotangent and the other trig functions, the pivot is back to the left center point. In the cotangent case, the pivot is not a point on the graph. For tangent, the pivot will be a point on the graph. But basically, there are 2 cycle shapes. The pivot is located differently for the 2 functions. All right. We're going to use the frame picapia method to graph equations of this type. Y equals a non-zero number times tangent or cotangent of a linear function of x, all plus d. Now, what are some modifications with respect to the sine and cosine graphs that we did before? Okay, well, we're going to have different cycles. We have different cycles. Sine and cosine had pieces of waves. Here we have snakes. Also, tangent and cotangent technically have no amplitude because remember, these snakes were infinitely tall. Instead, I'm going to talk about a frame amplitude, and that's given by the absolute value of A. So instead of amplitude, I'm going to refer more to a frame amplitude, which is half the height of the overall frame. So basically, the frame amplitude would be this height over here, half the height of the frame. This helps us get the quarter points on the graph. The period is given not by 2 pi over b, but by pi over b. Remember that the period for the basic tangent and cotangent functions, the period was pi in both cases. It was 2 pi for sine and cosine. Later on, when we graph something like this, where b is the coefficient on x basically, the period in general is given by pi over b. If b is negative, then you want to use the odd property of tangent or cotangent first. If b is not positive right now, then use the absolute value of b down below. The period is always positive. But for tangent and cotangent, we're going to use that the period is pi over b, not 2 pi over b, which is the case for sine, cosine, and also cosecant and secant. Now, when drawing a cycle for a tangent graph, remember that the pivot, PD, is going to be the central point of the frame, the center point. It's the left center point for all 5 of the others, including cotangent. That will correspond to the origin, or the origin used to be. Okay, let's now look at an example. Use the frame method if you wish. If you don't use the frame method, then give me all the information the frame method would have given me. Use the frame method to graph one cycle of the graph of y equals 2 tangent of 2/5 x all minus 3. There are infinitely many possible cycles, but the frame method will suggest one. Now, first of all, notice here that b, the coefficient on x, is positive. B equals 2/5, which is positive. That's great news for us, because if b were negative, we'd have to use the odd property for tangent or cotangent functions. If we had a negative 2/5 x, for example, then the negative sign we'd need to pop out. Here, b is positive, no problem. Remember that both tangent and cotangent are odd. Let's find the pivot. Where does the origin move to? What is the phase shift? Well, to find the phase shift, you set the argument here, 2/5 x, equal to 0. Where does 2/5 x equal to 0? Here, it's straightforward. X equals 0. This happens when x equals 0. Two-fifths x equals 0 when x equals 0. So there's no phase shift. There's no horizontal shift. If you want, you could add or subtract by the period, but there's no need to do that here. If the phase shift can be said to be 0, we'll use 0. Now, what about the vertical shift? We just pull that directly from here. It's this constant term on the right side. That's the vertical shift, -3. We shift the graph down by 3 units. So the origin is basically moved down to the point 0, 3. And remember, the pivot
-3
for tangent corresponds to the central point, the center point of the frame. 0 is here. -3 is over here. Here's P, here's D. The origin moves down 3 units. We're at the point 0, -3 for the pivot, the central point. Now from the -3, this is D now, how do we get the y-coordinate for the top line of the frame and then the bottom line of the frame? Well, the frame amplitude is 2. Remember, we look at the number in front of tangent here, a equals 2. That's the frame amplitude. There's no overall amplitude because the snake is infinitely tall, but the frame here has an amplitude. Half the height of the frame is 2. So, to get the y-coordinate of the top line, we take -3 and add 2. -3 plus 2. -3 plus 2 is -1. So -1 corresponds to the top line segment. To get the y-coordinate for the bottom line segment, we take the -3 and we subtract the 2. We get -5. So -5 is the y-coordinate for the bottom line segment of the frame. Okay, so we have a good idea of the y-coordinates we need to work with for the key points. Now, what about the theta, or in this case, the x-coordinates? We're back to x-coordinates. What about the x-coordinates? Well, first, we're going to need the period. How do we get the period? The period is given by not 2 pi over b, but pi over b. Remember, b is now positive. The period is given by pi over b. Pi over, well, what was b? The coefficient on x was 2/5. It was the 2/5 over here. Pi over 2/5. When you divide by 2/5, you multiply by the reciprocal of 2/5, which is 5/2. So we get 5 pi over 2. Pi divided by 2/5 is pi times 5/2. That's 5 pi over 2, and that's the period. Do we put 5 pi over 2 here at this VA? The answer is no, because 0 is not at the left edge, it's at the center. So we do not put 5 pi over 2 anywhere over here. Instead, we're going to use the increment. For all 6 trig functions, we cut the period into quarters. We take 1/4 of the period. 1/4 times 5 pi over 2. We multiply across. We get 5 pi over 8. That's the increment. That's the number that we're going to add and subtract in this case to get the various x coordinates for our frame. All right, at this point, I'm going to go straight to the answer. So we have 0 in the middle. 0 plus the increment, 5 pi over 8, is 5 pi over 8. That's the x-coordinate for this key point here. 5 pi over 8 plus 5 pi over 8 is 10 pi over 8. That simplifies to 5 pi over 4. Don't forget to simplify. You can see that 5 pi over 4 is half of the period, 5 pi over 2, because we're getting half the period from here to here. And then we could use symmetry about 0 to get the x-coordinates over here. This is negative 5 pi over 8. Over here, this is negative 5 pi over 4. It's convenient that we have 0 in the center. If the phase shift were not 0, if there were some phase shift, then we would actively have to subtract. We would subtract the increment, subtract 5 pi over 8, subtract 5 pi over 8. So where does the period actually come in? Well, if you want to do a check, the period is the distance, the total width. It's the distance between the two VAs here. 5 pi over 4 minus negative 5 pi over 4 is 10 pi over 4, or 5 pi over 2, the period. So the period is hidden in the graph here. Picapia. Don't forget the final A for picapia. Superimpose the coordinate axes. The x-axis, don't forget to put the x at the right end. The x-axis corresponds to y equals 0. Now, where's y equals 0? Well, 0 is above all these negative numbers over here. These are the y coordinates we picked up before for the key points. Y equals 0 is above the entire frame, in fact. Now, I'm not going to get a ruler. As long as you put the x-axis above the frame, above the -1 in particular, then I'm happy. The y-axis has equation x equals 0. Well, it's right through the middle here. Here's 0. Put the y at the top, not the bottom, put the y at the top of this vertical line. And we're done. We have one cycle for the given tangent function. We know the VAs are over here at x equals 5 pi over 4 and x equals negative 5 pi over 4. We could read off the points of these tic-tac-toe key points. And we have the axes here. By the way, one advantage for superimposing the axes at the end is that if we started by putting x and y axes, then it might be a struggle to try to locate these key points. We'd have to worry what quadrant are we in and all that. So it might actually be harder to fit these points into this coordinate system where the axes are already there. I think it's easier to do the axes at the end. Superimpose the axes at the end, but don't forget them. Don't forget to put on the x and y axes. But it's easier to put them on at the end. The x-axis has equation y equals 0. The y-axis has equation x equals 0. Now again, for all tangent graphs, I'm going to put the pivot at the center. If you choose to put the pivot at the left center, which you could do, then what's going to happen is that you are going to get a vertical asymptote in the middle here. So you're going to get half a snake here and half a snake here. And that's going to be ugly. That's going to work, but it's going to be ugly. Another way that you can do this is that in their trig classes, some students actually find the VAs first. Remember, we found the pivot, in particular the phase shift, P, by setting the argument equal to 0. We set 2/5 x equal to 0, and we got x equals 0. That was the phase shift P. Now, if you wanted to find the VAs first, well, you could set the argument 2/5 x equal to negative pi over 2, which is where the VA used to be, and at positive pi over 2, which is where another VA used to be, and solve for x. And then you'd get negative 5 pi over 4 and positive 5 pi over 4. But I think that's more work. It does work, but it's more work, I think, instead of just figuring out that the 0 is in the center here. For cotangent, by the way, the old VAs were at 0 and at pi. But again, I think it's easier if we place the pivot smack dab in the center and focus on the pivot. The phase shift P is obtained by setting the argument equal to 0 and solving for x. Here, we get x or P equals 0. There is no phase shift. There is no horizontal shift. Although if you wanted to shift by the period to the left or to the right, you get an appropriate cycle. Next up, how do we graph cosecant and secant functions? Next time.
Okay, actually, now's a good time for a break before we get to those funky graphs. So I have 8:06 right now. Let's come back at 8:17. Back 8:17. All right. So let's call a break here. So remember to mute before you eat or do anything else, right? I'll remember to record. Come back at 8:17 for the funky graphs, cosecant and secant. I'll see you then.
Hi, everyone. We're now going to graph cosecant and secant functions. And these are going to give us up-u, down-u graphs. That sounds kind of mean. So remember that cosecant of x is the reciprocal of sine of x. And when we're graphing y equals cosecant of x, which is in red here, we're going to consider the corresponding guide graph, which is when you replace cosecant with sine, or later on, when you replace secant with cosine. The guide graph here, y equals sine of x, is in black, and that's going to help us a lot. You should always graph the guide graph, or maybe 1 or 2 cycles of the guide graph before you try to graph the cosecant or secant graph. Here's the graph of y equals sine of x, 2 cycles. From here, we're going to graph 2 cycles for y equals cosecant of x. By the way, because the period for sine of x is 2 pi, the period for cosecant of x will also be 2 pi. That's the same for cosine of x and secant of x. The period will be 2 pi for these 4 basic trig functions. Okay, now remember, cosecant of x and sine of x are a pair of reciprocal trig functions. So let's go back to tangent and cotangent, and let's talk about the relationships we saw there. Remember that, informally speaking, 0 and undefined are reciprocals of each other in basic trig. So for example, when tangent is 0, when we have an intercept over here, that corresponds to a VA for the cotangent graph. When tangent is undefined, and we have a VA for the tangent graph, that corresponds to an intercept, a 0, for the cotangent graph. So the zeros or intercepts for one graph correspond to the VAs for the other graph, where the other function is undefined. Well, we have the same relationship between this black guide graph for sine of x and this red graph for cosecant of x. Where do we draw the VAs, the vertical asymptotes, for y equals cosecant of x? Cosecant of x is undefined when sine of x is 0. That is, we draw the VAs, which are dashed lines here, through the x-intercepts of the black sine graph. X-intercept for sine, we get a VA for cosecant. X-intercept, or 0, for sine, we get a VA for cosecant. Intercept goes to VA, intercept goes to VA, intercept goes to VA. You draw VAs for the cosecant graph through the x-intercepts, or zeros, for the sine graph, the guide graph. Okay, Now, between these VAs, we graph these up U shapes when the guide sine graph is above the x-axis, and we graph these down U shapes when the sine guide graph is below the x-axis. And that makes sense because remember, reciprocal functions have the same sign for the same value of x. Remember for tangent and cotangent. Remember for tangent and cotangent. Going back here. Tangent was positive when cotangent was positive, and tangent was negative when cotangent was negative. So for example, in quadrant 1, everyone's positive. Tangent is positive, and so is cotangent. In quadrant 2, tangent is negative, and so is cotangent. Positive to positive, negative to negative. So it makes sense that both the sine and the cosecant pieces will be either above the x-axis, like over here, or below the x-axis, like over here. Also, we get an up U shape. First of all, it makes sense that since we have a symmetric sine lump between the two VAs here, that this piece for cosecant will also be symmetric about this line. Why do we have an up U shape? Because when sine increases, its reciprocal function cosecant decreases. When sine decreases, its reciprocal function cosecant increases. They go in different directions. That was similar to what we saw with tangent and cotangent. Tangent had rising snakes, cotangent had falling snakes. So again, the features that we saw, the relationships between tangent and cotangent as reciprocal functions, we're also seeing here. The relationships between sine and cosecant. Again, when one is 0, the other is undefined. When sine is 0, cosecant is undefined. And since sine is never undefined for real values of x, cosecant is never 0. Notice that this graph for y equals cosecant of x does not have any x-intercepts. Cosecant of x is never 0. That's good to know. Secant of x and secant of x, by the way, are never 0. 0 is never in the range of these guys, the basic trig functions. Otherwise, the values have the same sign, positive to positive, negative to negative. If you look between the asymptotes and the intercepts, as one function increases, the other function decreases. That's why we have these up U, down U shapes for cosecant of x. They have the same period. It's 2 pi for both sine of x and cosecant of x, and also for cosine of x and secant of x. Now, what about these points where the graphs meet up? I'll put them in blue here. What about these intersection points between y equals sine of x and y equals cosecant of x? Well, that makes sense because, now over here, remember, cosecant is undefined when sine is 0. Now, what happens when sine is 1? Well, the reciprocal of 1 is 1, so cosecant of x is 1 exactly when sine of x is 1. Whenever the sine graph hits a y-coordinate of 1, the cosecant graph also hits a y-coordinate of 1. That's why the black graph and the red graph meet up at all these points on the sine graph where the y-coordinate is 1. Likewise, the reciprocal of -1 is -1. So cosecant of x is -1 exactly when sine of x is -1. So for every value of x where the sine value is -1, like here and here, cosecant of x, the reciprocal, will also be -1. So for this value of x and for this value of x, because sine of x is -1 here and here, cosecant of x is also -1 here and here. So that explains why the cosecant graph and the sine graph meet up at their max and min points. A max point for the sine graph corresponds to a midpoint for the cosecant graph. The period is the same for both. So, for example, we have one period between 0 and 2 pi radians. I'll erase the rest of these marks. We have one period between 0 and 2 pi radians. So on the sine wave, we get one cycle over here. A period is 2 pi radians. Now for cosecant, we pick up, I'll put this in orange, we pick up an up u and a down u. And we pick up a vertical asymptote right in the middle there, in addition to the two on the edges here. So a full cycle for y equals cosecant of x must consist of an up u and a down u, and you must indicate the nearby VAs in the vicinity of the up u and the down u. By the way, you could pick up half an up u, a down u, and half an up u, this sad face, that also counts as a cycle. But this here will count as our fundamental cycle, where we start with an up u here and then a down u here, because remember, our basic fundamental cycle for sine of x starts at the origin here. We're going from 0 to 2 pi. So our fundamental cycle for y equals cosecant of x will consist of this up u, this down u, and the three VAs in the vicinity at x equals 0, pi, and 2 pi. All right, so what about y equals secant of x? We basically do the exact same thing for its reciprocal guide graph, y equals cosine of x. Secant of x is the reciprocal of cosine of x. Secant of x is the reciprocal of cosine of x. Remember, cosine of x gives us an even function. The graph is symmetric about the y-axis. But notice here, this guide graph, y equals cosine of x, this is our guide graph. It's basically a horizontal translation of y equals sine of x. But cosine is even, so this graph is symmetric about the y-axis. Well, to get the graph of y equals secant of x, we use the same principles as before. We draw VAs through the x-intercepts of the cosine graph. Intercept for the cosine graph gives us a VA for the secant graph. Intercept to VA, intercept to VA, intercept to VA. And then we draw an up u, down u pattern. Up u when the cosine graph is above the x-axis, down u when the cosine graph is below the x-axis. So here, notice that we're getting one cycle here and one cycle here, but this time we get the sad faces I kind of mentioned before. Half an up u, a full down u, and half an up u. Actually, our fundamental cycle for y equals secant of x goes from 0 to 2 pi. We pick up this half of an up u, this down u, full down u, and this half of an up u over here. It's like a sad face. It's kind of weird looking, and also don't forget to put the VAs. It's kind of weird looking, it's almost like it's crying, but this does count as one cycle. This is the fundamental cycle for y equals secant of x. Again, we use the same basic principles as when we went from sine of x to cosecant of x. Like cosine of x, secant of x is an even function. The graph is symmetric about the y-axis. The period for all these will be 2 pi. All right. Next up, we're going to discuss vertical asymptotes, domain, and range. That's next time.
Okay, before we get to there, I call these the up u, down u graphs, which sounds vaguely rude, obscene almost. So this is my video for that. I thought it was kind of cute. Okay. Oh, really? It's a famous clip. Is that right? All right. Okay.
Hi, everyone. We're continuing with the basic cosecant and secant functions. As far as symmetry goes, remember that the old sine function was odd, so its reciprocal function, the cosecant function, is also odd, meaning that both graphs have the following property. They have symmetry about the origin. If you rotate either graph 180 degrees about the origin, you get the same graph. For the cosecant graph in red, for example, this red up U rotates to this red down U. Likewise, this red down U rotates to this red up U. Now the old cosine function was even. So its reciprocal function, the secant function, is also even. Those graphs are symmetric about the y-axis. The cosine graphs and the cosine graph and the secant graph are both symmetric about the y-axis. Okay, now what about vertical asymptotes, VAs? Well, take a look at cosecant of x, which is, remember, the reciprocal of sine of x. We have a VA when cosecant of x is undefined. And cosecant of x is undefined when sine of x, the bottom here, is what value? And sine of x is 0. So cosecant of x blows up when sine of x down here is 0. Well, where is sine of x equal to 0? If you look at the unit circle, sine of x corresponding to the y-coordinate on the unit circle corresponds to this east point and this west point. And these points correspond to integer multiples of pi. 0, pi, 2 pi, 3 pi, 4 pi, and so forth. And they're opposites, like negative pi and negative 2 pi. So we have vertical asymptotes if x is of the form pi n for all integers n. Likewise, the domain for the cosecant function is going to be the set of all x in the reals where x is not of the form pi n for all integers n. Now you might find this familiar. The domain for the cosecant function is the same as the domain for this cotangent function. And why is that? Because, look here, cosecant of x by the reciprocal identities is 1 over sine of x. Now, we had a problem when sine of x was 0. What other function has the property that when you tear it apart, you have sine of x on the bottom? Well, cotangent of x, which by the quotient identities equals cosine of x over sine of x. So cotangent of x and cosecant of x are both undefined. They both blow up when sine of x, this bottom guy, is equal to 0. So it makes sense that they both have the same sets of VAs and they both have the same domains. If you look at the graph of y equals cosecant of x, up here, the VAs are at x equals 0, pi, 2 pi, and so forth. These are the same VAs as for y equals cotangent of x. Same VAs, and also the same domain, The domain for the cotangent function, the domain for the cotangent function was the set of all values, real values of theta that were not of the form pi n. Likewise, the domain for the cosecant function is the same. The domain for the cosecant function, all real values of x in this case, where x is not of the form pi n for integer n. Similarly, let's take a look at the domain for secant of x. Well, secant of x, by the reciprocal identities, secant of x is equal to 1 over cosine of x. Well, secant of x is undefined. It blows up when cosine of x equals 0. And what other function had cosine of x in the bottom when you tore them apart? Tangent of x was sine of x over cosine of x. Both tangent of x and secant of x blow up when cosine of x is 0. So secant of x and tangent of x have the same domain. we have a problem when cosine of x is 0. Cosine is the x-coordinate. Where is x-coordinate 0? At the North Pole and the South Pole. So both secant and tangent have a problem when x is of the form pi/2 plus pi n, where n is integer. It can be written like this. Now notice that when you write the domains and the ranges for the 6 basic trig functions, that's a great exercise, these sets tend to pair up. Again, the domain for cosecant of x and the domain for cotangent of x, they're the same. Likewise, the domain for secant of x and the domain for tangent of x, they're the same. Up here, we have a problem when sine is 0. Over here, we have a problem when cosine is 0. For example, at pi/2. For secant of x, like for tangent of x, we have VAs at x equals pi/2 plus pi n. So for this graph over here, we have VAs, like for tangent of x, we have VAs at pi/2, 3 pi/2, and so forth. And therefore, the domain consists of all real values that exclude those places where we have VAs, that exclude pi/2, and so forth. Now, what about the range? It turns out that the range for secant of x and cosecant of x are the same. These two pair apart. The ranges for the two functions. It's this over here. It's a high-low game. And why is that? Let's take a look at cosecant of x up here. Look back at the range for sine of x. The range for sine of x goes from, these are y coordinates, goes from -1 to +1. The closed interval from -1 to +1 is the range for sine of x. That's the range for sine of x. Now, if you look at the range for cosecant of x, we want the y coordinates that we pick up on the red graph here. And it turns out that we take the range for sine of x and we turn it inside out. We get these high positive values and we get these very negative values. Over here, we get all positive values greater than or equal to +1. Down here on the down U pieces, we get all negative real numbers up to and including -1. The range for both cosecant and secant, again, we have the positive numbers from 1 off towards infinity, the negative numbers from -1 down towards -infinity. But remember, we follow the real number line. So we indicate this range as parenthesis, -infinity. In fact, you could think of it as a vertical axis. From -infinity up to -1, from -infinity up to -1, and then from 1 up towards infinity. A union of these two intervals, high-low. These positive values, union with these negative values. These positive values, union with these negative values. High-low. We're turning the range for sine of x inside out, like so. Now, cosine and secant just give horizontal translations of these, but the picture with the y coordinates, that just translates over. So we have the same range for both sine and cosine, and the same range for both cosecant and secant. Again, it's the high-low game. Cosecant of x and secant of x have the same range. It's a union of two intervals, these positive values and these negative values. Notice that what number is not in the range? What number in here is not in the range? 0. 0 is not in the range of either cosecant or secant function. Cosecant of x and secant of x are never 0. And that's helpful. For example, if you have a trig equation, you can easily divide both sides by cosecant of x without things like domain issues. All right. Next up, we're going to transform these functions and these graphs next time.
All right, so any questions about these basic properties for cosecant and secant? Because we finished the basic 6, we're going on to these transformations. All right, and then I have a cool video to show you. All right.
Hi, everyone. We're going to finish section 4.6 by graphing transformed cosecant and secant functions. In the beginning, let's start with y equals sine of x, that classic odd sine wave. Now remember, how do you graph y equals cosecant of x? Y equals cosecant of x, it's the up u, down u graph. And we would have VAs at x equals 0 and x equals pi, for example. Now, what happens if we were to put 2's in front? Y equals 2 sine of x. What would happen? The amplitude doubles. We have a vertical stretch by a factor of 2. What if we do the same over here and put y equals 2 cosecant of x? Again, we get a vertical stretch away from the x-axis by a factor of 2. And once again, the purple graph attaches itself like a parasite or a remora to the green guide graph, the sine graph. What if we put a 3 in front of the x? We get a more hyper sine wave. The period is cut down to a third. What if we put a 3 here for cosecant? Again, the purple graph attaches like a parasite. It's the same up u, down u pattern. And the max point for the green graph here matches up with the midpoint for the purple graph. Same for here and here. Over here, max on purple is min on green. Same for here and here and here. What if we substitute x with x minus pi over 4? That leads to a horizontal shift. Well, if you do the same for the cosecant equation, same thing. The purple graph attaches like a parasite. What if on the green graph for sine, I put a big old +1 at the end? That raises the graph by 1 unit. How about the purple graph? +1. So take a look at this. Just by replacing sine with cosecant, if I can graph the corresponding sine equation, then I can basically play the whole up u, down u game to graph the corresponding cosecant equation where I replace sine with cosecant. The same properties hold for cosine and secant. So basically this tells me that if I wanted to graph a more general cosecant function like this, the key thing is to graph the corresponding guide graph, in this case with sine. And if I know how to graph the version with sine, then I play the whole up u, down u game to get the graph I want for cosecant. And again, the same goes for cosine and secant. So being able to graph the guide graph, the sine graph here, is really helpful in graphing the graph we actually want. All right. So in general, how do we graph something of the form y equals a non-zero number, times cosecant or secant of a linear function of x, all plus d? For example, how do you graph something like this? Use the frame method, or not, just give me all the info, to graph one cycle of the graph of y equals -3 secant of 4x plus pi, all plus 2. Again, the critical thing here is to be able to graph one cycle of the guide graph when you replace secant with cosine. Well, very fortunately, we've already done that. In section 4.5, we graphed one cycle of the corresponding guide equation, y equals -3 cosine of 4x plus pi, all plus 2. And this gives us an opportunity to review this example, which we had to rush before. We're going to review the frame picapia method for this cosine equation, and then we'll show how to get the secant graph from the cosine graph over here. Let's review picapia. All right, for this cosine function or equation here. Now, picapia, the frame method. The first P is for pivot, which is my term, pivot, but this corresponds to P comma D, the point that the origin moves to. The pivot is the point P comma D, the point that the origin moves to. The origin moves to, basically. P is the horizontal or phase shift. P is the phase or horizontal shift. And D is the vertical shift. Oops. I'll retype this. P is the phase horizontal shift. D is the vertical shift. Okay. Now D is very straightforward. We can just grab this constant term over here, that's D. That's the vertical shift. The phase shift, so D is 2. The phase shift or horizontal shift, that takes more time. You can either use a factoring method or set this equal to 0 and solve for x, which I think is easier. But if you want to use the factoring method, you take the argument here, 4x plus pi, and you factor out a 4. B. This is B actually. B is 4. You factor out B. If B is negative, you absolutely have to factor out at least a negative 1. But here we have 4x plus pi. We factor out B, the 4. When you factor, you divide. We have 4 times the quantity, x plus pi over 4. And what is x plus pi over 4? It's x minus negative pi over 4. The phase shift P is negative pi over 4. You do a sign flip from here to here. The phase shift is negative pi over 4 from the factoring technique. Again, if that seems confusing, the easy way to do it is to take this argument, 4x plus pi, set equal to 0, and solve for x. Subtract pi, we get 4x equals negative pi. (4x equals negative pi), and then divide both sides by 4, you get x equals negative pi over 4, which again gives us the phase shift. Now, you have the right to add or subtract the period any integer number of times. Now, if this value of x were extreme, like 1,000,000 radians or something, then we would probably want to use the period to knock it down. Keep subtracting the period until you get something as close to 0 as possible. Technically, the phase shift is the horizontal shift, the most appropriate horizontal shift that's closest to 0. But in practice, I will take any horizontal shift that'll work. But technically, the phase shift is supposed to be the horizontal shift, the appropriate horizontal shift that's closest to 0. If necessary, add or subtract the period an integer number of times. Here, negative pi over 4, that's as close to 0 as we can make it, as it turns out. The period turns out to be pi over 2, and we're not going to get anything better. So we're going to take negative pi over 4 as our phase shift, our horizontal shift. So the pivot, the point that the origin moves to, is P, the phase shift, negative pi over 4, comma D, 2, the vertical shift here. We knew D was 2. That's the point that the origin moves to. All right. Now for the frame method, the pivot corresponds to the left center point of the frame. Only tangent puts it at the center point. For every other trig function, the pivot goes at the left center. Now, we have here a cosine function on the right side, function of x. Now, notice that b is positive. That's important because if b is negative, you better take care of that right off the bat using the even property for cosine. And you might have to do some factoring in here. But since b is positive 4, that's not a problem. But first of all, we need b to be positive. We know cosine is over here, and we have a is negative 3, which is negative. So we have cosine and A being negative. What kind of cycle does that correspond to? Cosine and A is negative, given that B is positive. Normally, a cosine cycle looks like that, but since A is negative, we flip it around, and it looks like this hill or pimple. That's the cycle shape we want, the C in picapia, A at the end. What about the amplitude? Cosine graphs have amplitudes. Is the absolute value of A, the absolute value of -3 is +3. That's the half height of the frame, or in this case, the graph. The period, which is the second P in picapia, that's period. For everyone except tangent and cotangent, it's 2 pi over b. We assume b is positive. What was b? Well, b, remember, is the coefficient on x. Again, if b were negative, then fix it so that b is positive. But b here is +4. It's the coefficient on x, and it's positive. So the period is 2 pi over 4. That simplifies to pi over 2. But remember, we're going to use the increment more directly. That's always 1/4 times the period. 1/4 times pi over 2 is pi over 8. So let's use the frame method. Here we go. Picapia. Picapia. I'll put that here again. Picapia. First P for pivot. Where's the pivot? It's right here at the left center point. In this case, the point is not actually a point on the graph, on the pimple, the hill. Now the pivot is at the left center. We found that the pivot was at -pi over 4, 2. P here, D here. That's where the origin moves to. C for cycle shape. It was this hill. We get these 5 key points. Midpoint, inflection point. It's no longer an intercept. It's just an inflection point. Max point, inflection point, midpoint. A for amplitude. The amplitude was 3. 2 plus 3 is 5. 2 minus 3 is -1. These are the y coordinates of these key points, these quarter points. The P was for the period, but what we use directly is the increment, I for increment. It was pi over 8. Over here, we start at -pi over 4, but the increment is pi over 8. Increment was pi over 8. It was 1/4 of the period. Remember, we calculated that up here. It was 1/4 times the period, pi over 8. So let's put this in terms of eighths. Remember that 1/4 is 2/8, so -1/4 pi is -2/8 pi. We can write this as -2 pi over 8. If we put things in terms of eighths, it makes the addition much easier. We're going to keep adding the increment to get each new coordinate on this grid, this frame. A common denominator helps. -2 pi over 8, which is the x-coordinate of this point here, -2 pi over 8 plus 1 pi over 8, the increment, is -1 pi over 8. This is simplified. -1 pi over 8 plus 1 pi over 8 is 0. We're very thankful for that. In fact, we could use symmetry now to get pi over 8 over here and pi over 4 over here. Or you could just keep adding pi over 8. 0 plus pi over 8 is pi over 8. 1 pi over 8 plus 1 pi over 8 is 2 pi over 8. That simplifies to pi over 4. Where does the period come in? The width of this cycle is the period. Pi over 4 minus -pi over 4 is pi over 2. And that's the period. Period is the width of the cycle. It's pi over 2. which is what we figured out up here. The period was pi over 2. And that's where the period is embedded in the graph. It's this right x-coordinate minus this leftmost x-coordinate. It's the width of this cycle. Do not put the period here if the number here is not 0. All right, picapia, that last A. Let's add that to the notes. Picapia, A for axes. Superimpose the coordinate axes. The equation of the x-axis is y equals 0. So we want to put this x-axis between y equals -1 and y equals 2. Again, I won't get a ruler, but make sure that the x-axis is between these two line segments on the frame, between the -1 and the 2. And put the x on the positive end, the right end, not the left end, the right end. A lot of students forget that. The equation of the y-axis is x equals 0. Luckily, we have 0 right here. The y-axis is right here, but the y on top in the positive end, not the negative end. For some reason, a lot of students like to put the x here and the y down here. No, you put the x to the right, the y on top. And there, you have one cycle for that cosine guide graph. But we're not done. Because remember, the original problem was a 4.6 problem. We wanted to graph one cycle of that. But once you get this, you're 80% of the way there. All right, now here I'm squishing the frame a bit. The frame here was kind of big. I'm going to squish it. So here's the frame, this thinner rectangle. It's more squat, it's shorter. This hill is the same as this hill. I'm just squishing it. So based on the red graph and the frame, how do we graph one cycle of the original secant graph? This is the actual secant graph I want. The VAs go through these midpoints, these inflection points. They're no longer intercepts on this red hill, but they're still inflection points. So you put a purple VA through here and through here, through the inflection points, these middle points on the red hill. And then you go up U, down U. Here we only have room for half of a down U until we hit this VA. Here we can get a full up U between the two VAs here. Over here to the right of this VA, we only have room for half a down U. But together, in purple, we have one complete cycle for that secant function, and we have the VAs that are in the vicinity. And lo and behold, together with these coordinates, these axes, these labeled axes, if you look at the purple graph, together with the purple VAs here, we have a graph for one cycle of that secant function in purple. And the guide graph helped a whole lot. We pick up a max point for the purple graph, a VA, this min point on this U, another VA, and another max point over here on this down U. Yes, these points down here are max points for these purple pieces, these pieces of down U's, and this point on the y-axis is a min point for this up U piece. So this point up here, this y-intercept, is a local minimum, actually, a local minimum point. And these points here are local maximum points, even though they're technically lower than this point here. So it's all about the guide graph. If you can graph one cycle of the guide graph, then to graph one cycle of the corresponding cosecant or secant graph, put VAs through the inflection points for the guide graph, and do your up U, down U game. And that's that. That was a big adventure. Next, in 4.7, we'll look at inverses for these trig functions. Until then.
Okay, now first of all, I mentioned that the purple graph was like a parasite or a remora. If you remember the Desmos things I had earlier, right? Like these Desmos graphs, right? It's like the up U, down U graphs were like attaching themselves. So I'll go ahead and go over here. Yeah, so I think of the purple graphs, The purple graph here, this cosecant graph, is like a bunch of remoras on this green shark here over here. Okay, now we're going on to the inverse trig functions. All right.
Next, in 4.7, we'll look at inverses for these trig functions. Until then. Hi, everyone. This is section 4.7 on inverse trig functions. And we're going to start with the graph of y equals inverse sine of x or arc sine of x. Actually, you might prefer this arc sine notation because it's less confusing. And these two mean the exact same thing. The problem with this notation is that a lot of people think that inverse sine of x means 1 over sine of x or cosecant of x. Now, 1 over sine of x is cosecant of x, as we saw before, but this here does not mean reciprocal. It means function inverse. That's confusing because we're used to thinking that x to the negative 1 is 1 over x. So when we see something like this, we think reciprocal, that the negative 1 is an exponent. But here, the negative 1 is not an exponent. It's just a superscript that indicates function inverse. So again, the inverse sine of x, or arc sine of x, is not the same as the reciprocal of sine of x, or cosecant of x. These are two completely different functions. They're related to sine of x in different ways. Cosecant of x is the reciprocal, the multiplicative inverse of sine of x. But this here, the inverse sine of x, represents the function inverse of sine of x. That's different. These are two very different functions. In general, f inverse is not the reciprocal of f. That's not typically the case that we have equality. All right. Now, in the beginning, we have y equals sine of x. Let's consider the graph of y equals sine of x, the sine wave. But there's a problem when we try to invert this and get an inverse function, inverse sine of x. The problem is that even though this graph passes the VLT, the vertical line test, so we have a function here, the problem is that it fails the HLT, the horizontal line test, which means that this function is not one-to-one. It's not invertible. It fails the horizontal line test. I can take a horizontal line here that intersects the graph in more than one point. In fact, infinitely many points. So what we need to do is that we need to restrict this sine wave. We need to restrict the domain of sine of x in such a way that we follow two conditions. What should this restricted domain be? It should be an x interval on which the sine graph, first of all, passes the HLT, the horizontal line test. That means we can take an inverse. That's an inverse function. And it has to be as tall as the original graph, meaning that the range is the same as before. Because I could say, hey, the origin, the point 0, 0, if I grab that, that passes the HLT. But that's pretty lazy. We would like something bigger than just a point. We would like something as tall as the original graph that has the same range, but a piece of the graph that will pass the HLT. So we want a piece of this sine wave that's as tall as the original graph. It has the same range, but passes the HLT, the horizontal line test. Now, we all agree across the planet that we start at this point, negative pi over 2, comma negative 1. And then where would we stop? Well, we want to pick up the entire range, so we have to keep going, going, going. We want the entire range, and we're going to stop where? We're going to stop here, at this point here, at pi over 2, comma 1. Because we want to capture the entire range for the sine function from negative 1 to 1. Technically, it's a new function here because we're restricting the domain. For the original sine function, the range was from negative 1 to 1. The domain was all reals, but we're now restricting the domain to this closed interval from negative pi over 2 to pi over 2. We have the same range as before. Now, we don't want to go any further because then we're going to we're going to fail the horizontal line test. So we don't want to go any further than this point. Okay, so we all agree that we're going to grab this red piece of the sine wave from this point here to this point here. And it goes to the origin, 0, 0. So then, how do we go from this restricted sine function to an inverse sine function? We can invert this because it now passes not just the VLT, but the HLT. So remember a key basic principle. Actually, there are 3 basic principles. The domain of one function becomes the what of its inverse function. The domain of a function, a one-to-one function, like this now, becomes the range of its inverse function. Second, the range of this function becomes the domain of the inverse function. And also, the idea that the point A comma B on the original graph becomes what point on the inverse graph? The point B comma A. The idea being that inputs and outputs switch. So based on this red graph here, how do we invert this red graph to get the blue inverse graph? I'll take a copy of my notes here. And here we go. Again, we switch the domain and the range. Let's look at this grid. The restricted domain for sine of x, we just determined that on Desmos. The restricted domain, the x-coordinates go from negative pi over 2 to pi over 2. The domain for the restricted sine function becomes the range for the new inverse sine function. Likewise, the range for both the original and the restricted sine function, the y-coordinates we pick up, went from negative 1 to positive 1, the y-coordinates. The range for the sine function now becomes the domain for the inverse sine function. The domains and the ranges switch. And these are all closed intervals. So observe, the old domain went from negative pi over 2 to pi over 2. That's the new range, from negative pi over 2 to pi over 2. By the way, pi over 2 is about 1.6. So this graph here, if you're using equal scaling on the x and y axes, the graph here is a bit taller than it is wide, if you're using equal scaling. The range on the old sine function here, this is the restricted sine function, from negative 1 to 1, the range on the sine function now becomes the domain on the inverse sine function. So the y-coordinates here, from negative 1 to 1, now become the x-coordinates here, from negative 1 to 1. That's why I'm putting these tick marks on the x and y axes. Domains and ranges switch. Let's take a look at things point by point. The point 0, 0 lies on the old graph, so the point 0, 0 lies on the inverse graph. The point negative pi over 2, comma negative 1 lies on the old sine graph. By old, I mean the restricted sine graph. The point negative 1, negative pi over 2 lies on the inverse sine graph. Remember, AB goes to BA. We switch the coordinates. Likewise, the point pi over 2, comma 1 becomes the point 1, comma pi over 2. A few other observations. First of all, notice that the restricted sine function is still odd. The inverse of an odd function is odd. That is true. This blue graph, this inverse graph, is also symmetric about the origin. Second, the red graph here is going up. The restricted sine function is increasing, and the inverse of an increasing function is also increasing. This graph is also going up from left to right. For example, remember temperature back in section 1.9. So as things got warmer, both Fahrenheit and Celsius temperatures went up. Fahrenheit and Celsius temperatures went up together, or they went down together. X and Y both went in the same direction. Same thing here. X and Y go in the same direction here. X and Y go in the same direction here. Now, at the endpoints here, the graph goes flat. We have sort of one-sided horizontal tangent lines over here and over here. I'm putting those in green. The horizontal tangent lines here become vertical tangent lines over here. Now, bear in mind, these green tangent lines are not actually part of the graph, but I'm using that as a visual aid. These two green tangent lines. The horizontal tangent lines on the old graph become vertical tangent lines over here, meaning that even though the red graph went flat near the endpoints, the blue graph becomes steep near the endpoints. Also, the concavity changes. This graph goes from concave up to concave down. This graph goes from concave down to concave up. But if you remember that the graph gets steep near the endpoints, you don't have to remember that. That's just natural when you graph it. The big picture. Notice here, this red graph has finite length or arc length. This is the entire red graph here. The blue graph here, this is the entire graph of y equals inverse sine or arc sine of x. It has finite arc length. And you can find the length of this in calculus. All right. Now, before we go on, I'd like to show you this in Desmos. Again, here's a graph of y equals sine of x. If you put the line of reflection, y equals x here, notice that x and sine of x are very close near the origin. That's no coincidence in calculus. What if we graph y equals arc sine of x? Well, it might be kind of hard to see, but the piece of the blue graph from this point to this point, if you reflect it about the green line y equals x, you get the purple graph. It's a bit hard to see. By the way, instead of arc sine of x, you could actually do sine with the -1 superscript. It's the same graph. Now, actually, if you care about the coordinates of the inverse sine graph, remember, domains and ranges switch. So notice that here, the domain for the restricted sine function was from -π/2 to π/2. The domain for the restricted sine function now becomes the range for the inverse sine function. Y equals arc sine of x, the arc sine function. The range now goes from -π/2 to π/2. Here's the point -1, -π/2. Here's the point 1, π/2. And likewise, the range here from -1 to 1, the y coordinates, becomes the domain here, the x coordinates, from -1 to 1, from here to here. Domains and ranges switch. Which means, again, these fractions of pi, they're better for the x-axis when you're talking about the original restricted sine function, but they're better for the y-axis when you're talking about the inverse sine function. We'll talk about the inverse cosine and inverse tangent functions, their domains, ranges, and graphs next time.
Okay, any questions so far? Okay, because if you understand the deal with inverse sine, then the others are pretty natural. Any questions so far? All right, so I think this is our last video, I think. Yeah.
Hi, everyone. We're continuing with our trek through 4.7 on inverse trig functions. We're now going to consider the graph of y equals inverse cosine of x, or arc cosine of x, which means the same thing. Now, over on Desmos, let's take a look at y equals cosine of x. We need to grab a piece of this cosine wave that is as tall as the original cosine wave, so we keep the same range, but it's got to pass the HLT, the horizontal line test. We all agree that we start here at the point 0, 1. Now, we can't move around this point because we're going to fail the HLT if we move to the left and to the right at the same time. So we're going to start at 0, 1, and we're going to move to the right. And where do we stop? we have to pick up the entire range, we're going to stop here. Because then we'll pick up the entire set of y-coordinates from -1 to 1, the entire range for the original cosine function. We can't go any further because if we go any further, we're going to start failing the HLT. So we all agree that we're going to grab the piece of the cosine graph from 0, 1 to pi, -1. And we're going to restrict the domain to the closed interval from 0 to pi. Now, remember that when we go from a one-to-one function, which this now is, to its inverse function, the domains and the ranges switch. So remember, going back up here, and I'll put this down here, the domain for the red graph is from 0 to pi, the x-coordinates. That's the domain. The domain for the original function, meaning the restricted cosine function, becomes the range for the new inverse cosine function. The old range, the y-coordinates from -1 to 1, that becomes the new domain, the closed interval from -1 to 1. These are all closed intervals here. Again, for a one-to-one function, like this restricted cosine function, and its inverse function over here, the domain of one becomes the range of the other, and vice versa. Also, the point AB becomes the point BA. So when we graph the inverse graph, I'll put these side by side, the restricted sine graph is
Cosine.
right over there. The corresponding inverse graph for the inverse cosine function is on the right. 0, 1 goes to 1, 0, which is on the right over here, the rightmost point. This x-intercept at pi over 2, 0 now becomes a y-intercept at 0, pi over 2. The point pi, -1 becomes the point -1, pi. Again, domains and ranges switch. The domain from 0 to pi becomes the range from 0 to pi on the y-axis. That's why this graph never falls below the x-axis here, because the values in the range are non-negative. Likewise, the range from -1 to 1 here becomes the domain from -1 to 1 here. Like for the case of sine and inverse sine, the original red graph goes flat near its endpoints, so the inverse cosine graph goes steep near its endpoints. And this is the entire graph. You're looking at the entire graph for y equals inverse cosine of x. The tangent line there, the tangent lines here in green, you may not want to actually graph. They're just there to indicate steepness. But you are looking at the entire graph. It has finite arc length. The inverse of a decreasing graph or function is decreasing. So x and y are going against each other this time. Now this graph is symmetric about this x-intercept, so this graph is symmetric about its y-intercept. Bear in mind, this restricted cosine function is not even because we're not allowed to go to the left of the y-axis. All right. So here is the graph of y equals inverse cosine of x, or arc cosine of x. We can go to Desmos. Remember that the fractions of pi tend to go on the y-axis. Now, y equals arc cosine of x. Finite arc length. We go from this point, -1, pi, to this point, 1, 0. And it's going down. All right. Now, what about a restricted tangent function and its inverse? Let's consider the graph of y equals inverse tangent of x, or arctangent of x. Well, the graph for y equals tangent of x is a zoo of snakes, and we all agree that the piece that we want to invert is this middle piece over here that goes to the origin. So we're going to invert this proud rising snake. Remember, we have VAs at x equals negative pi over 2 and x equals pi over 2. So when we invert this proud rising snake, what do we get? Well, again, the domains and the ranges switch, and guess what the VAs become? The VAs become HAs. So the VAs at x equals negative pi over 2 and pi over 2 become HAs now at y equals negative pi over 2 and pi over 2. The rising snake here is tall and proud. The snake here is rising. The inverse of an increasing function is increasing, but it's not so proud. It's a lazier snake. It's more of an S graph, kind of like for cube root. This graph in red gets steeper and steeper near the VAs. This graph in blue gets flatter and flatter as it approaches the HAs. There's only one really key point here on the red graph, 0, 0, and it goes to 0, 0. There are other points like 1, pi over 4, but we tend not to use the frame method here. We tend not to identify the quarter points so much on inverse trig graphs. Again, the restricted domain here, you see, is from the open interval, from negative pi over 2 to pi over 2. The range, the y-coordinates we pick up, all real numbers. All y-coordinates, all real numbers are picked up as y-coordinates. So again, the domain is the open interval from negative pi over 2 to pi over 2. That becomes the range for the inverse tangent function. The y-coordinates we pick up here. The x-coordinates here in red are the y-coordinates here in blue. The range here, the y-coordinates we pick up here, all real numbers, becomes the domain here, all real numbers. And notice, unlike the other two guys, this inverse tangent graph is infinitely long. It has infinite arc length. It goes on forever and ever. The range for restricted tangent, all reals, becomes the domain for inverse tangent. These sets switch. On Desmos, when you graph y equals arctangent of x, it goes on and on and on, approaching the HAs at y equals negative pi over 2 and pi over 2. All right. Now, you can reflect the middle tangent snake about y equals x to get the inverse tangent. Lazy snake, the S graph, is kind of hard to see, but you could reflect about y equals x. In the next video, we're going to talk about a shortcut for finding ranges. Before we do that, I want to mention that for inverse cosecant, inverse secant, and inverse cotangent, we're not going to deal with the ranges so much of those, or the graphs, because they're controversial. In fact, you might have different ranges in a pre-calculus book versus a calculus book, because they're different purposes. So we will not discuss the ranges for inverse cosecant, inverse secant, and inverse cotangent, because pre-calculus and calculus books will differ. The ranges for inverse sine, inverse cosine, and inverse tangent, as we discussed before, these are not controversial, and we'll discuss a shortcut for remembering them in the next video.
Which will be next week, although it is, around. So you know what, let's end the videos for today. You can get through the homework on 4.6. We just, in 4.7, I just introduced to you these basic inverse trig functions. I'll discuss these more next time. We're going to finish up chapter 4 next time. In fact, we'll go back and review the bits of 4.2 through 4.4 that I missed on inverse trig and word problems. So we're going to finish chapter 4 on Tuesday, all right? Okay, so at this time, I'm going to stop the videos and I will take questions. Some of you are going to leave. Have a good weekend. But this time, I am going to take questions. Okay, I'm going to keep recording. So I'm going to keep recording. So unless you want me to stop the recording, I'll go ahead and keep recording. Again, students like these extra bits here. It helps them out. Okay, so yes, for some of you, thank you and good night. But I will stick around. Okay, if you have any questions right now, I will stick around. Okay. Also, there's email and office hours, but you know, any questions? Any questions? So I'm going to pause now. I'm going to come back in 2 minutes at 9:30, and I'll let you gather your thoughts. Okay, so let's see. So we have a couple of questions here in the 4244 block. This, let's see. Okay, all right. So let's take a look. 4244 number 8. Oh yes, yes. Interesting problems here. Okay, so let's see. Now, is there a particular letter you'd like me to focus on, or I could kind of talk about the ideas here? It's based on the idea of the unit circle. Is there a particular letter that you'd like me to try out here? Or I can just kind of move along. Let's start with, let's start with C. Okay, so unless you have a preference, go ahead.
No, that was 20C in this actually.
There's another student.
Oh.
Yeah. So 8C. Okay, this student was asking for number 8. So I'm just kind of okay. So do you want to say 8C for now, and then okay. So let me do 8C for now, and then I'll discuss D and E briefly, and then I'll get to 20. Okay, so 8C. Okay, so consider the unit circle. And these are quadrant 1 angles, so I'm going to just focus on quadrant 1. All right. Now this won't be to scale because I want to get the idea here. So I'll do this in 2 different colors. 70 degrees, that could be like this over here. That's probably a little bit steeper on me, yeah. And not that I'm being that accurate anyway, but okay, so here we have the point corresponding to the 70-degree angle. All right. And then here, whoops, here we have the point corresponding to the 80-degree angle. Okay, so when I think tangent, I think what word? It starts with an S. When I think tangent, oops, move zoom toolbar. Okay. When I think tangent, I think slope. Okay, in fact, a student really impressed that on me. So I'm asking here, which has the greater value? So here's my question to you. Which would have the greater slope? The slope for the red point, 70 degrees, or the slope for the blue point, 80 degrees? Which would have the greater slope? Notice both these slopes are positive. The tangent values are both positive. I think we're going to get the greater slope, the greater tangent value for 80 degrees. Wouldn't you agree? The slope is going to be greater for the 80-degree radius here, right? So that's going to be my answer there. So for sine, that's an issue of y-coordinate. For cosine, that's an issue of x-coordinate. For tangent, it's an issue of slope. Okay. For D and E, I'll give you a couple of hints. All right. In quadrant 1, because we're in quadrant 1, sine increases, right? Follow the sine wave, like on Desmos. In fact, even Desmos might help here. If you look at y equals sine of x, notice that in quadrant 1, sine is increasing, all right? But if sine is increasing, what's the reciprocal doing? What's the reciprocal doing? Sine increases, but its reciprocal, cosecant of x, decreases. And that's a key hint there. As for part E, I'll give you another hint. the cofunction identities. What do the cofunction identities say? By the cofunction identities, actually, it might be easier if I, let's see. It might be easier if I, well, how do I want to do this? No, okay, I'll leave it here. By the cofunction identities, all right, the cosecant of 10 degrees is equal to the secant of the complement. What is the complement of 10 degrees? 10 degrees plus what is 90 degrees? 10 degrees plus 80 degrees is 90 degrees. And that's going to be a hint there. So basically in part E, you're comparing the secant of 70 degrees with the secant of 80 degrees because these two guys are equal by the cofunction identities. So I've given you various hints here, which will help you to solve this problem. And of course, we'll have time next week and I guess the Tuesday after that homework session to discuss this further. But I'm giving you some key hints here. Try to run with these and see if you can get these. Right. Feel free to ask questions further in chat or by voice. Okay, so any questions there? Oh, okay, so I'll keep these notes on here. So next we have, oh, you're welcome, yes. So next we have 20C, right? And thank you for being patient. Okay, 20C. Ah, yes, okay. Assume that sine of theta is 0.3, where theta is acute. So that means we have a quadrant 1 angle, and it's acute, all right? Find cosine of theta using the Pythagorean identities. Yeah, it helps to know we're in quadrant 1 because we know that the trig values are both positive. That's going to help here. Okay, so let's use the Pythagorean identities here. Now, what is the key basic Pythagorean identity? Sine squared x plus cosine squared x equals 1. And I got to put the squares here. Sine squared x plus cosine squared x equals 1. And let's see if I can get rid of these periods here. All right, move these over. All right, so this is the key basic Pythagorean identity that you should know until your grave, right? Sine squared of x plus cosine squared of x equals 1. That's your key basic Pythagorean identity. All right. Now, in fact, if you wish, you could even start by plugging in right now. So if you want to plug in sine of theta equals 0.3 right now, you can do that. All right. So instead of sine squared x, we can just say the square of 0.3, right? Sine of x is 0.3, right? We're assuming sine of theta is 0.3, but we need it squared, all right? Oops. All right. Plus the cosine squared x guy equals 1. Okay, any questions so far?
No.
Questions so far? All right. I'll just write in the 2 again. Okay, so I'm taking the basic Pythagorean identity, and then instead of working this out with the word sine, go ahead and plug in. Well, oh, by the way, it's not x, it's theta, but don't worry about that. It's theta. But sine of theta, right, is 0.3, all right? That's being squared, plus cosine squared theta, right, is 1. So again, replace x with theta in your homework. All right, okay. Now the square of 0.3 is 0.09, actually. Okay, plus that cosine square guy equals 1. All right, so all right, so the square of ignore the little periods. The square of 0.3 is 0.09. All right, plus cosine squared x equals 1. Well, the 0.09 I can now subtract. I'll do this in red. I can subtract 0.09 from both sides. Oh, now I see what the issue was. Yeah, okay. I will go ahead and do that though. Because I remember before I worked with fractions, but okay. So we subtract 0.09 from both sides. Okay, so then these go bye-bye. All right, and we're left with cosine squared x. Okay, cosine squared x, green. Okay, cosine squared x equals, okay, now 1 minus 0.09 is 0.91, but now I remember why students got confused here. Because the thing is, if you want to present exact simplified values, sometimes fraction form is better. So instead of 0.91, to get the form I had in my answers, it's better to think of this as exactly 91 over 100, right? 0.91 is the fraction 91 hundredths, right? And when you're taking square roots, it's actually easier to think of it that way, actually. All right. So then, okay. So then, what can cosine of x itself be? So technically, we're supposed to use the square root method. All right. So according to the square root method, we have plus or minus the square root of. Okay, and to get the answers to my answers on the website, the square root of the fraction 91 over 100.
Oh, okay. That's why I didn't convert to the fraction.
Right, yes. Yeah.
I see why do you get that answer.
Right, yeah. And I had to remind myself, because I realized in the middle, oh, that's the issue that students raise. Because remember, if an instructor is really insistent on a simplified exact answer, it might be safer to deal with fractions. And sometimes I have to remember that too. By the way, when you work this out, see, basically on the top, you're going to get the square root of 91. 91's prime, so you can't really make it nicer. What's the square root of 100? The square root of 100 is 10, right? And remember, we're dealing with an acute angle here. What sign do we take here? Well, we take the positive. Basically, we knock this out. And this is the exact value you get for cosine of x.
Excellent. Yeah, now I see why.
Oh, yes, yeah. Yeah, and I had to remember what the trick was. Yeah, I remember here, I converted to fraction, right? Okay.
Thank you.
Oh, you're very welcome, yes, thank you. It helped remind me too. Sometimes I have to remember too.
I get to that point, 0.9, but I didn't see why there.
Right. So it's good to be flexible. So if you're looking at the back of a book or online, sometimes they give you the exact fractional form. Right.
Yeah. Thank you.
You're very welcome. Anything else? Yeah, it's just you and me right now. So yeah, anything else on your mind?
No.
Or if you want to wait a couple minutes, I can come back to you.
What about B?
Part B. Okay, so in part B, it's the identity. It's the cofunction identities. Okay.
Oh, is that the cofunction? Okay, I see.
Yes. Because really, what this comes down to is the cosine of this equals the sine of the complement. But guess what? Plain old theta is the complement, right? When you add these together, you get pi over 2 radians. So a key hint was, the key recognition was understanding that this represents the complement of theta, right? These are complements. Cofunctions of complementary angles are equal. And the answer is therefore good old 0.3 here.
Oh.
Right. But recognizing that it was tricky for people because they look at this and they go, oh my gosh, what's going on? Recognize that that is the complement of theta. So the cofunction identities.
All right, thank you.
Okay. Now, bear in mind, if you wish, I can come back in a couple of minutes, or if you need to go, no, I understand.
No, that's it.
That's it. Okay. So I'll see you later on. Have a good weekend.
Thank you.
Okay. Take care. Bye bye.